spaceflight. In the pioneering days, it was mainly a matter of national prestige. Technological progress was driven by the wish to be the first. The space race resulted in an impressive number of launches, especially when it came to military reconnaissance and communication satellites. Today, commercial and scientific applications dominate in spaceflight. We have now become accustomed to many services provided from space in our daily lives: communications, weather forecasts, television, remote sensing of the environment and navigation. Our activities in space have left traces behind. To date, there have been some 5,000 successful satellite launches, and certain orbits are at risk of becoming congested. About 17,000 man-made objects are currently being regularly monitored from the ground. Some 10,000 of these objects are fragments created by more than 250 explosions and collisions that have occurred in orbit. Explosions are caused by energy reservoirs that remain unused upon completion of a mission. Only 7% of the monitored objects are functioning satellites. The effect has been particularly evident in the low Earth orbit region. This extends to a height of about 2,000 kilometers. Two-thirds of all known artificial objects can be found in this comparatively small region. However, also here, they are far from evenly distributed. For most missions, near polar orbits between 600 kilometers and 1,200 kilometers altitude are used. For this reason, the highest collision risk can be found in the vicinity of the Earth's poles. The Earth's upper atmosphere below these altitudes prevents debris from remaining in space for long periods of time. The objects are slowed down by the atmosphere, causing them to lose height and burn up on re-entry. Orbits above 1,200 kilometers are too far away for Earth observation missions and communication applications. They are therefore used considerably less. Collision warnings are issued regularly for satellites operating at the critical height in polar orbits. During routine operation, about 10 objects every week come within 2 kilometers of such satellites. In recent years, ESA has had to carry out about 3 collision avoidance maneuvers per year. A particularly critical situation occurred on the 21st of January 2010. The calculated flyby distance to a disused rocket upper stage was only about 50 meters. The probability of a collision was greater than 1 to 80. The maneuver to avoid a collision was only carried out half an orbit before the determined approach epoch, and increased the clearance to a safe distance of 130 meters. However, most of the artificial objects in space are uncontrolled and cannot be influenced. This means that the majority of collisions cannot be avoided using such evasive maneuvers. There have already been 4 major collisions in low Earth orbits. The most serious of these collisions was the one between an Iridium satellite and a defunct Cosmos satellite on the 10th of February 2009. The satellites collided at a relative speed of approximately 42,000 kilometers per hour. This resulted in the creation of an additional 2,000 items of debris that can now be tracked from the ground using radar. These debris will disperse at differing speeds over the course of time due to the effect of Earth's gravitational field. The Iridium fragments are less affected, meaning that they disperse somewhat more slowly. This compact cloud of debris regularly results in a high risk of collision for satellites operating at this height. Many of the critical flybys occur in the polar regions, where all of the near-polar orbits overlap. This is also where the collision between Iridium and Cosmos occurred. Such collisions currently take place about once every 5 years. The more objects accumulate in orbit due to spaceflight activities, the more frequently such collisions are going to occur. In future, more and more collisions with fragments from earlier incidents are going to occur. This collisional cascading effect was already predicted some 40 years ago. The exponential increase in the number of objects is extremely difficult to slow down. If the current number of launches continues and no countermeasures are taken, the collision rate will eventually be 25 times what it is at present. This would make spaceflight in the important low Earth orbits almost impossible. Today, most of the debris is still caused by accidental explosions due to unused fuel on board. However, the problem can be alleviated by so-called passivation measures. These include depleting unused fuel, venting pressure tanks, and switching off batteries. Collisions can also be prevented if satellites are removed from heavily frequented orbits at the end of their missions while they are still under control. If they are brought down to a height below 600 kilometers, they will only remain in space for about another 25 years before re-entering the Earth's atmosphere. Collisions with a few items of debris remaining in this area are very unlikely. The passivation of objects and the reduction of their residence time in space are measures that stem from recommendations by international experts. They have already been incorporated in the guidelines of many major spacefaring nations. ESA also applies such measures. The Earth observation satellite ERS-2 that provided data about our planet for more than 16 years was moved into a lower orbit in August 2011. The orbit altitude was reduced from 770 kilometers to 570 kilometers using several maneuvers. The density of the atmosphere here is about 10 times higher, meaning that the satellite will decelerate more rapidly and quickly lose orbital height. ERS-2 will therefore re-enter the Earth's atmosphere through natural mechanisms within 15 years and pose no further collision risk. Most of the remaining fuel on the satellite was used up by additional depletion maneuvers. Finally, batteries were disconnected and radio contact was shut down. ERS-2 is now completely passivated and will remain physically intact until it re-enters the atmosphere. Measures such as this need to be applied consistently and globally to limit the growing amount of space debris. However, it is going to take some time before this is implemented for all missions. Unfortunately, such measures can only limit the growth but not prevent it. Objects that are already in space still represent a risk, and their number will further be increased by future launches and collisions. Even if no more launches took place, and the space debris situation was left to its own devices, simulations have shown that the number of objects will not decrease but increase. This is caused by cascading collisions between resident objects and fragments of prior collisions. That scenario indicates that the critical density of objects in the low Earth orbits has already been exceeded. Active intervention is the only way to reduce the present critical density to a sustainable level. The active removal of large and uncontrollable objects is a considerable technical challenge associated with high development costs. The effectiveness of the measures particularly depends on careful selection of the target objects, whereby the following 3 criteria must be met: a high collision risk, a large mass, and a long residence time in space. As we have seen, the collision risk is highest in near-polar orbits between 800 and 1200 kilometers. This is the area that will see the highest growth rates, even if all preventive measures are rigorously implemented. This area therefore deserves a closer look. For this purpose, the individual object orbits need to be broken down into their respective heights and inclinations. Now, several source regions for an increased number of collisions can be identified within the polar orbits. Collisions are particularly likely in locations where many objects have already accumulated in similar orbits. Active intervention in such regions would be especially effective. The severity of the contamination depends on the mass of the colliding objects. Hence, ideally, large objects should be removed first from these regions. The higher the orbit, the longer debris from potential collisions will remain in space. Efforts should thus concentrate on critical regions in higher altitudes. In order to allow spaceflight to continue without restriction in future, about 5 to 10 of these objects need to be actively removed every year. This is the only way to fully stabilize the space debris population in space. However, there is a long way to go before the first service vehicle can actively remove objects. There are many technical problems to solve. Approaching an uncontrolled target object is a major challenge. This involves the avoidance of collisions with the target and determining its attitude motion. Because the target object is no longer transmitting telemetry data, the position needs to be actively determined from the ground. This requires the use of radar systems. An initial impression of the attitude motion of the object can be gained from Earth using, for instance, the Tierra tracking and imaging radar located in Germany. The final phase of approach requires the use of relative navigation, for which purpose LiDAR or radar systems can be used. The exact attitude can then be determined using a camera. The method that is used to capture the target object can be chosen depending on certain conditions such as rotation rate, the structure of the surface, and the size of the object. One possible method is to use a robotic arm to grab a suitable element on the surface of the target body, stopping the motion and berthing the object. The motion can be dampened by a clamp, which can then provide a secure frictional connection. Even the casting of a net would be feasible. This would avoid the need for direct contact with the object, which can then be towed away. These different methods permit the use of powerful thrusters. This allows the service vehicle and the target object to re-enter the Earth's atmosphere together in a controlled manner. Controlled re-entry would take place above unpopulated areas and is the ideal solution. If controlled re-entry is not required, other options are available. The object could be removed from the critical region and disposed of at lower altitudes. It would then re-enter the Earth's atmosphere due to natural air drag at a later date. The initial orbit lowering can be achieved, for instance, by solid rocket motors that are attached to the object. They would first stabilize its attitude and remove it independently afterwards. A passive method of lowering the orbital height is also available. The size of the surface can be increased considerably by attaching a sail, which will increase the atmospheric drag and therefore accelerate the orbital descent. Another idea is irradiation with an ion engine. To do this, ions are accelerated to fast speeds by an electrical field. These efficient low-thrust engines are ideal for long, continuous orbital changes. The constant bombardment of ions onto the surface of the target causes a momentum transfer to the object. Direct contact is therefore unnecessary. Before the active removal of objects can start, there are a number of legal issues to resolve. According to international space law, the responsibility for any debris object or abandoned satellite remains with the owner, even though it is no longer functional. All risks associated with the mission are therefore the responsibility of the owner of the service vehicle and the owner of the target object. The selection of the target objects concerns all major spacefaring nations. Active removal measures must therefore rely on an international consensus. The technical and legal challenges must be overcome now. The active removal of space objects will only become commercially viable after a certain time. Nevertheless, the initial steps need to be taken soon in order to effectively stabilize the situation in space. Active removal remains the only option for ensuring that spaceflight under current conditions will remain possible in the future.